Hello? Yeah. So we'll continue talking about surface integrals. So as I said the last day, these surface integrals, they will uh, mainly in physical applications, they will be used to compute the mass of uh, this kind of surfaces that have some kind of density of mass. So make sure you understand when to apply the appropriate integral. And of course, they will be the same formulas for the moment of inertia and the torque, what is it, yeah, and the center of mass, right? It's the same formulas. So let's do an example of this computation. Compute the integral over S ds, where S is the sphere. Okay. So here you need a parametric representation of the sphere. So we have parametric representation. We have the so this is we found this the last time. So now the radius is 1. Cos theta y is equal to sine phi sine theta, and z is equal to cos phi. And of course, the range, the domain is phi between 0 and pi, theta between 0 and 2 pi. Okay? So no, I'm not gonna do the competition again, but we got last example that our phi times our theta, this is equal to, remember we got the we got a squared times sine phi, but now a is 1, so okay. So So the integral over s y ds is equal to integral from 0 to pi, 0 to 2 pi. Okay, so now we are computing this surface integral. So on the surface, y is equal to, if I use this one, right? Because we are parameterizing with phi and theta. So for some phi and theta, y is equal to sine phi, sine theta, r phi, r theta, dA, right? No, I mean, speaking carefully, this is equal to d. And d is always the domain you'll get there to describe all the surface. Now, sometimes you may choose to go to coordinates, polar coordinates, sometimes, in this case, it's a rectangle, so it's from 0 to pi, 0 to 2 pi. Now, if I use the formula of this one, which is sine phi, now I got sine phi square sine theta d phi d theta, right? Now, this is a usual integral. Now, this one sine squared is 1 over 2, 1 minus cos d phi times integral 0 to pi sine theta d theta, okay? Which is equal to 1 over 2 phi minus 1 over 4 yeah, and 1 minus 4 sine. Okay, so no, wait a minute, hold on. Okay. Any questions? So, as I said, for applications, it's the same as I told you yesterday. Okay. So, if a thin sheet has the shape of a surface S and density, okay? In this case, density will be some function that gives you how much mass you have per unit area. At the point is it's some function rho x, y, z, because we're in the 3D plane, then the total mass is okay. And as I say, the center of mass is x bar and again, the same idea applies. This is the point where you're in equilibrium if you want to balance it. Okay? So, so here is the thing. You already know this kind of computations before. You already did this kind of computation before when z was the graph of a function. So now I'm gonna do three more examples, and each one has its own advantage. Yeah. So yeah. So I'm gonna do an example where example evaluate this integral if s is the part of the plane z equal to 1 plus 2x plus 3y that lies above the rectangle Okay. So here's the thing. You can parameterize this surface. Uh, right? You have the normal vector, and you can do a lot of work to get a parameterization and do the R5, right? And then cross product with R theta. Who is this now? Okay, so just the one who's just joined us right now, like, you made me laugh because of the emoji you have. Okay, so you can parameterize this plane, and you can apply the same formula, but you already know what is the surface of when you have a graph of a function. Right? I mean, you can prove it. I mean, it's not hard. I mean, what is a parameterization? I mean, I'm gonna do it like really quickly. I mean, but this is like, I'm gonna do it in blue. So that, I mean, you can parameterize using x and y. So what would be the parameterization? It would be r of x and y, right? It would be x, y, and z, which is x, y, and 1 plus 2x plus 3y. And then x are between 0 and 3, and y is between 0 and 2. So that's a parameterization. And then you can do the same. Our x would be 1, 0. Let me just keep it like del xz, whatever this gives. And then you can take this one, it's 0, 1, del z, del y, right? And then from these two, you can compute our x times our y, take the norm, which will be I, J, K, del, no, 1, 0, del z, del x, 0, 1, del z, del y. And if you take the norm of it, you're gonna find the vector. This is 0, 0. And it's gonna give you the vector dz, dx. For g, it will be minus dz, dy. And then for k, it will be plus 1. Right? So if you take the norm of this one, it's 1 plus dz dx squared plus dz dy squared. But this is exactly the formula. Remember the formula for the area. Well, that's exactly it, because what is ds? ds is just the the element of the surface area. So when you have ds, right? So you could apply this directly. When you have a graph, you can just use this one without going through this. But you can do it. I mean, it's your choice. But see, because so the ds is just the element of the surface area, which is, remember, which is what 1 plus dz dx squared plus dz dy squared, and you have to multiply by dA, and now you have to integrate over the projection on the xy plane. So that's exactly what you can do here. So here will be ds will be 1 plus, so what is dz? So the integral here x squared y z ds over the surface is, sorry, x squared y z ds is the integral x squared y z. Now what is ds? ds is 1 plus dz dx squared plus dz dy squared dA, right? Because when this is not here, right, when we don't have a function here, what is left is actually just the surface area of the of what you have, right, or the surface, right? So you will have this formula, which is the one you used before, right? Remember, right? When you have a function, you just multiply this very tiny piece of area by some function. And then the D here, it's always because when you parameterize with X and Y, your domain, it's no longer, I mean, you can move it into UV plane, but now it has a concrete meaning. It's the projection on the XY plane, right? When it is parameterized using UV, that's another story because UV, they will live in another space, which is the UV plane, and that's just your parameterization space, right? It has no real meaning. I mean, it's not a projection, it's nothing. It's just like, remember, it's like, for example, for the sphere, the domain was a square, 0 pi, 0 to pi, and then you got a sphere, right? The square is not a projection of the sphere on the surface. See, so these are two different things. When you have a parameterization, you have a parameterization space, you've got to work with the domain B of your parameterization space. Now, when it's a graph of a function z, you have two parameters, x and y, and they provide you with an easier visualization of the domain, right? Which is the projection. Because you are moving around that projection to describe z. So here is all the computations here now. You have to substitute whatever you had. Now what is z? Z is 1 plus 2x plus 3y. Now this is 1 plus 2. Why is it to the power 4? 4, 9. 9 plus 4 is, yeah. Okay. Now that the dy is from 0 to 2, right? Was it? Yeah. Make sure you have the right limits, depending on which order you're gonna start with. Okay. Okay, here there is nothing special with this integral, it's just polynomial. So you have to do it carefully. Sometimes I'm just gonna give you the answer because there is nothing here special. It's just polynomials. Okay, so now next example is gonna be a little bit challenging. It's another level. Now the next example is a surface that you have. Now what is it that we did right now so far? We had a surface, which is a sphere. We had a parameterization of it right away. And then we have the surface, which is a graph of a function. And we realize that it's the same formula that we know. Now, this example is a bit challenging because, look, now evaluate the integral over S z ds, where F is the surface with sides. So we have three sides. S1, which is the cylinder, x squared plus y squared is equal to 1. S2 is the disk, x squared plus y squared less than 1 in z equal to 0. And S3 is the plane z is equal to 1 plus x. Okay? So here is a graph of the surface. So we have the disk, okay? That's the cylinder. We have the disk, x squared plus y squared, this is 1. And this is z, right? This is x and y, z. This is x, and this is y, and this is z. And then lastly, we have the plane, okay, z, that is gonna go like this, right? It's a kind of plane that is gonna cut kind of like this, right? Okay, so maybe I need to, so it's kind of, right? It's a plane that goes like this, right? So, so it's a plane that goes along the x. So what's the right way to, ooh la la. I'm not sure how to describe it in my notes, but in my notes it's not accurate. In my notes it's not accurate, but because it's not a, oh no, actually no, no, it's a plane that, no, it's a plane that goes like this. Yeah, so it's, it makes sense. Okay, it makes sense. So it's a plane that goes, remember, what is this? This is a line, right? It's a line like this in the ZX plane, right? Now, when you have this plane that is gonna be intersecting the inter, inter, intersecting right, intersecting the cylinder, you're gonna be an ellipse. Yeah, but it doesn't go through the origin, so it's a bit more. So the intersection will be above. You can find the intersection, but this is the intersection. Okay. So we're talking about this. Oops, sorry. That's the surface. Yeah. So yeah, so you will have to do the integral over all the surface, and that's why I said it's gonna be challenging because you will have to parameterize three sides. But don't be scared. We're gonna go through it slowly, but don't be too much intimidated by this. You'll see it's not that. Okay, so we'll have the you will have the side S1. And then why is it that I make a lot of typos in my notes? This one, now S2, and S3 is, what is S3? Yeah, S3. Okay, so the surface is actually three surfaces. The first one is the top one, which is the intersection of the plane with the cylinder. The second, okay, the first one is the cylinder itself. The second one is the disc. And the third one is the top, the lid. So the part of the plane, circular, you know. We have that S is S1, union S2, union S3. So we evaluate the integral S Z ds on each on each surface on each surface on each side, and we add up the results. So that's the way it is done, right? If you have a surface area there is a lot. There is the inclusion. There is a union of 3 or 4 or whatever you have surfaces. How many surfaces you have? You've got to do it on each side, and then you add all of these up. So here, so you have to go slowly. Like now, we go on S1. Okay, so on S1. So you forget about the others, and you just do it on S1. Now you just have to do what we did in the examples before, except that you have to parameterize this one. So what is this one? This one is a cylinder, right? So go back to the example while I introduce the cylinder. So the parametric equation of this one is, so here actually we are using, if you think about it carefully, we are using cylindrical coordinates in the sense that we are using the angle. I don't want to mess up with the graph here. So actually we are using the angle here, theta, and then z. No, those were the cylindrical coordinates. So if you want to describe a cylinder, you need two variables. So one will be rotating around the xy plane, and then for each theta, you can move along, right? So it will be circles, and then you move a little bit, you do circles, you move a little bit, you do circles. So that's gonna give you the cylinder, right? So we'll go back to the example we did the last time, and you'll see. Well, we did it with the, it was a reverse cylinder. It was Y. It was along the y-axis. Now it's along the z-axis. So you have to reverse the variable. So x is cos theta, y is equal to sine theta, and z is equal to z. Those are the variables. You can use v here. I mean, it doesn't matter. You can use v. Sorry. Why is it that? Oops. Those were the. So you can use v here, but you can use z also. It doesn't really matter. So the only new thing here is, if you keep it like this, it'll give you a cylinder, but depending on what is the values of theta and z, it will give you cylinder. I mean, it will give you kind of cylinder, right? So if, for example, if it's 0 and 2 pi, and here it's 0, 1, like for example, this is not the case. I'm gonna make it write it in red. If it's 0 to pi, and here it's 0, 1, it will not give you this oblique cylinder. It will give you the cylinder that is like this. That's it. But you don't want that. You want the top surface is not a flat one. We are integrating over 2ds again. I am not sure I understand what you say. Over 2ds. We are not integrating here. We're just trying to find the parametric equation of the surface. I think it is a z. This is z, it's not 2. Is this your question? Oh, so we evaluate. Oh, yeah. No, it's z. Yeah, it's z. okay? And make sure it's capital S, not small s, okay? Because that would mean an arc length curve, right? So make sure when you write down or your assignment or whatever you wanna, right? Do not confuse the equator. Okay. So as I was saying, if you take 0, 1 here, it's not gonna give you the right one. So here, it's gonna be really strange for some people, but the domain will be still 0 to pi, right? Because in any way, when you're moving around here, you're still going around, right? This is how you describe. The only thing is, okay, so for some z, you fix some z, you go around 2 pi. Right, now, the way you describe this is for some theta, that's the way actually you do it. You start with 0, theta equal to 0. Now 0 is between something and something. Now you go around with some theta. Now z is gonna vary as you're gonna go around, right? In the first case, when it was between 0 and 1, for each theta, you had the same z. The description of the surface was like for each theta, you go from 0 to 1. And then from each theta, you go from 0 to 1, right? And in this case, you get the whole cylinder. That was the first one I gave you, like the one that is flat. Now the problem here is for each theta, the range for z is gonna depend on theta, right? So the first thing to do is, what is z? For each, z is between what and what? Well, it is between 0, right? For each theta, I go from 0 to what is the top surface? It is a plane. It's on the plane. So the last one you're gonna hit is z equal to 1 plus x, right? Depending on your x. Oops. Depending on your x, right? It depends on x. Now, if you wanna write it in terms of theta, what is your x? X is 1 plus cos theta. That's x. So now I have that z for some theta. I go from 0 to 1 plus cos theta, right? And same thing for every theta. So now we're gonna vary z, and that is gonna be the right thing. So as you see, this is not a projection, this is nothing, like this is in the theta and z plane. It's just the parametrization space. So it'll be, I don't know, it'll be for, you do it. I think it'll gonna be some surface here, like on the zy plane. It's some domain here. You can write it, right? I think it's a circle here. I think it's a circle. It's a circle, but it's not centered at the origin. Okay. All right. So, but you still apply the same formula. So r theta z is equal to cos theta sine theta z, right? So this is the parameterization of the surface, right? But be careful here. G is not a function of theta. It's just for the integration. Z is still a free variable. Okay? It's just if you want to describe, you have to stick in the domain, V. That's just the description of the domain. Right? So R theta is minus sine theta cos theta 0. And R phi is 0, 0. No, sorry, this is not phi. Z 1. Okay. So R theta times RZ. I'm gonna let you do the calculation. It's supposed to give you cos theta, or look at my notes if you want. Cos I plus sine theta P. So the norm of R theta times the norm of RZ is cos theta squared plus sine theta squared, which is 1. Now we apply. So the integral of the surface on S1 x ds, we apply the formula. Okay. Now this is your domain D. It's the integral over the domain D of, this is Z, of Z R theta R phi dA. Now the domain is from 0 to 1 plus theta, and theta from 0 to 2 pi, Z 1 dz d theta. Okay. And this will be equal to an integral from 0 to 2 pi, 1 over 2, 1 plus cos theta squared d theta. Okay. And this one is, we're gonna, from 0 to 2 pi, 1 over 2, 1 plus 2 cos theta plus cos theta squared d theta. And this is 1 over 2, the integral from 0 to 2 pi, 1 plus 2 cos theta plus 1 over 2, 1 plus 2 theta d theta. And this is 1 over 2 theta plus sine plus 2 sine theta plus 1 over 2 theta plus 1 over 4 sine 2 theta evaluated between 2 pi and 0, which is equal to 3 pi over 2. Is it? Yeah, 3 pi over 2. Okay, so make sure you understand this example. It's very important. Don't, okay, spend some time to review it. Okay, now it's done. So you remember this one. Now on S2. Now the surface S2 is the plane. Okay, so what is S2? The surface S2 is in the plane Z equal to 0. So, I mean, you don't have to do anything here because, yeah, you can. You can do the same thing. Why did you multiply R with Z? R? Which R? Phi R theta. You mean here? Sorry, this is a private message, so no, people are not seeing this. So, the student is asking, why did I multiply this? Well, this is just the definition. Go back to the definition. Right? The definition of a line integral is 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 um, remember that was the ds. Yeah. So when you have that was the ds. That was the element of the surface. Remember, we approximated this one. We approximated this one. The element of the surface. We approximated it with that's what I did here. Right? This is the ds. This is the ds. So the ds is approximated with this one. So when you go to the limit, right? This is a notation. ds is actually ru rv dA. Okay, right? And I did it here too. ds is always, you compute r phi r theta, you multiply by, and then dA, and then you integrate over d, which is the domain of the parameterization here. All right, so S2 is actually, remember, S2 is this disk here. It lies on the surface, on the plane XY, but with Z is equal to 0, right? So here you don't have actually anything to do because you can do ds and compute dy, d phi, which in this case is going to be really easy because it's just a plane, and then try to it's a disk, right? So you can parameterize with theta and r, and r will be from 0 to 1 and theta from 0 to 2 pi, and that will be your domain. But you don't, but anyway, by the end of the day, you're gonna have to evaluate z on the surface, right? But what is my surface here? It's a disk, and it lies on the plane z equal to 0. So at the point on the surface, it's always 0. This function is 0 on the surface. Because remember, what we have here is always a function that is evaluated on the surface. So z is equal to 0. So you are integrating 0 over the surface ds. So you don't actually have to do any work. It's going to give you 0 anyway. Okay? So for S2 it's easy. Now for S3. For S3, you have to parameterize that the 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 surface, right? On S3, what is the surface? The surface is, right? So here I'm gonna use the last example. The surface, this this is the part of the plane z equal to 1 plus x, right? Now you can parameterize this using x, y, and z, but as I said the last time, now the domain of parameterization will be the projection because you have a graph of a function. So now, if you want to really describe the whole surface, you are projecting here, right? You are projecting on a, it's a projection here. So the right description here will be the domain will be this one. That will be the domain. So this will be the domain for this one. So, right? So concretely speaking would be, this is the plane of the plane z is equal to 1. I'm gonna again do it by, but the reason I don't want to do it with the R and all of that, because for the graph of functions, you don't need R's and you don't need actually to compute any, because you don't need actually to compute any cross product. You just need to know what is the range of X and Y such that my surface is described with X, Y inside the disk, right? So if you take the plane and you take the projection of this ellipse on the XY plane, it's gonna give you the circle here, the disk. So for the graph, whenever you have a z equal to something, you can just apply the formula without any cross product. If you want to, it's okay, right? But it's just an easier way for you to just apply the formula. So so the integral, yeah, please ask me questions if this is too fast. So the integral of it, so it's z ds, right? So what is, so now z is equal to 1 plus x. What is ds? ds is one, it's the surface of the surface, the area of the surface, which is 1 plus dz dx squared plus dz dy squared dA. And now the domain D is the projection, right? Right? That would be your new parameterization domain. So this will be x squared plus y squared less than 1, 1 plus x. You compute dz, you compute dy, it will be 1 plus 1 plus 0 dA. Okay, now it's an integration over a domain. Now it's a disk, and whenever you have a disk, you go to polar coordinates. See, so now everything's kind of gathered together, right? So it's 1 plus r cos theta, r dr d theta from 0 to 1, and d theta from 0 to 2 pi. Why is, yeah, it's a square root 2 here. Yeah, just do it. So here is 0, and here it's 3 pi over 2, and then here it's square root of 2 pi. So the integral over s. Let me just write this one, and we're going to take a break. Z ds is the integral over s1 z ds, the integral over s2 z ds, the integral over s3 z ds, which is 3 pi over 2 plus 0 plus square root of pi, which is 3 over 2 plus square root of 2 pi. So that's the right, so that's the answer. That's the answer, all right? Okay, so it's a long calculation, but make sure you understand it. Okay, so let me take a break for now. And if you have any question, please ask me right now. Go over it right now if you want over the break. And let me know. Okay, welcome back. So this ends the section of the first type of surface integrals. So now we're gonna start with the last topic of the class, of which deals with surface integral. In the this will be pretty much the last thing you're gonna learn in this class. So and then there will be some results that is gonna gather all of the things you know so far, called curls, conversions, surface integrals, oriented surface integrals. So let me first start with an oriented, the last type of surface integrals you'll need. And you'll see it's not that much different from a normal surface integral, the one we just introduced, but you will see. So let me talk about oriented surfaces. Okay. So oriented surfaces are some kind of surfaces that you can say what is the outside of the surface and what is the inside of the surface. Okay, that's the intuition behind it, right? If you look at it in a certain point of view, you can say this is the outside and this is the inside. So if you have, for example, a surface, right? Okay, in the 3D, okay, take a point and then let me see. So you can assign to each point the normal vector n, right? There are usually two normal vectors because what is a normal vector? Remember, it's the at each point you know now that there is a tangent plane. You know how to compute it. right? This is there is a tangent plane here. So the normal vector is the normal vector to that plane. There's only one tangent plane. So there are actually two normal vectors. The one that goes in one direction and the other one that goes on 180 degrees uh, from the first one. There are two types of normal vectors. So you can do that. You can assign to each point a normal vector, right? You can assign to each point a normal vector, right? Right. But you're not allowed to move. You cannot just decide to just a little bit. You cannot decide. So here's the thing. If you decide that the point just next to this one, you gotta assign the other one, what will happen is this is not gonna give you an orientation because we would like that the normal vector will move continuously when you move around. So if suddenly you change the orientation when you move around the surface, right? If you choose this kind of orientation on the surface, this is not gonna be a nice orientation because suddenly you're gonna get the other one. You're gonna get the other side. So, and basically what this normal vector says is, this is the outer surface, right? So you cannot just say, okay, I'm on the outer surface and then just suddenly I get inside, right? So it doesn't mean anything, right? So you've gotta be consistent with your choice. So you have to assign normal vectors and they're gonna move. Of course they're gonna move. They're not gonna be all in the same direction, but it's gonna move continuously for nice surfaces. So an oriented surface, so if a surface, if given a surface, you can choose these normal vectors such that when you move around the surface, it moves continuously, then we say that this is an orientable surface. All right? So we're gonna write this. If it is possible to choose a normal vector and at every point x, y, z, so that n varies continuously over S, then S is called an oriented surface. And the given choice of n provides S with an orientation. Okay. So there are two possible. So for example, I could have chosen the other one, right? And this one, right? And that would be a perfectly legitimate orientation, right? As long as I stick with the continuity of it, uh, right? There are always two possible two choices of orientation. Now you might ask, well, isn't it true that we always can do that? Like you can always choose n and it's going to be continuous later. Well, the reality is there are some surfaces so that it's never possible to do that. So here's an example of this kind of surfaces. So this is a surface where you can choose the vector here. You can choose n to be this vector, and you can go and it's going to be continuous here, right? It's going to be continuous. You can keep doing this, but as you're going to move around, you're going to get inside, and then you're going to keep, and then you're going to give, and then you're going to have the other one, the other direction suddenly. So this is not continuous because you are actually on the same. You're actually on the same point. Ah, come on, come on. I really hate this app. So you're actually on the same. I mean, you just moved a little bit from that point, and then suddenly the orientation changes abruptly. So you can never choose an orientation on this Mobius sphere, right? Because you can suddenly get inside. So there is no inside, there is no outside of this surface, right? If you tell me that this one is the inside, this is the outside, then suddenly you will be telling me that it's the outside, right? Because then when you assign n to that on the other side, then you are telling me that this is the new outside. So this one becomes the inside, right? So if you start by telling me, okay, this is the outside, right? This is the outside. Then you go around, you go inside, and you assign n in the other direction. So now this is your new outside, which was the inside. You see, so there is really no inside, there is no outside. So that's the thing with the Mobius strip. There's no inside, there is no outside. So this is what they're explaining here. All right, but fortunately enough, we're not going to be dealing with this kind of surfaces. We're going to be dealing with the other surfaces that they have outside and inside. Okay. Suppose that S is given by the graph of a function z equal to gxy. Then S is parameterized by R X Y okay. So RU, RV, this is the same calculation I did the last time. It's minus, no, it's RX, RY, oh, now I'm not sure which one I said. There's a typo. So it's Rx. So it's minus dx I minus dy g plus k. Okay. So because we have a plus here, right? So a normal vector is given by, okay, so how do you, let me see. Because our x will be on the tangent plane, our y will be on the tangent plane. So when you take the scalar product, you're gonna get r x times ry. So this will be normal to the plane that is tangent, right? But you have to normalize by square root of the norm. The square root of the norm. So that you get a normal vector that is a unit one, right? And because, right, so because we are on the x, y plane, so because the y component here is positive, this is gonna give always the outer, it's right, so you're gonna move on the z-axis, so it's gonna be always the outward orientation. So there are two choices for n. So we're gonna choose this one as, we're gonna call this one the upward orientation, where there is a plus one. Remember that minus n is also a good choice for the normal vector. So but it's gonna give you minus k. But we will call this one the upward orientation. So when you have a question where you get take the surface, blah, 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 with the upward orientation. It means that when you evaluate the normal vector at a point, take this one. Don't take the other one, which is the minus k. So because k because the k component is positive, this gives the upward orientation okay? So this is for a graph of a function. When S is given by a parametric representation, we obtain a unit normal vector by the formula, which is basically the same one I use for the graph, but it's just for the graph of a function, we have an explicit formula. But this one will depend on the parameterization, right? And as I said, it doesn't really matter. In this case, there is no way I can tell you which one you choose. You have to go with the exercise, right? In a lot of cases, there will be closed surfaces, so you will know which one. Um, okay, okay, thank God, we're gonna be on time. I think so. Okay, let's do an example. Okay, okay, so now we actually need not the whole cross product, not just the norm. Recall that r phi times r theta. Remember when you did the calculation, it gave us this. Okay, and so here there is a magic that will happen because this one will vanish for phi equal to 0 and pi. But it's going to be canceled out when you're going to divide. So we're going to divide this by the norm, right? It will give sine phi cos theta I, and then sine phi with this one, which will give sine phi sine theta, and then this one with this one will be cos phi, and this is nothing else but the radius r over a, right? So concretely speaking, you have the sphere, right? And it will be, this is r. So at this point, it will be r, but normalized by the radius. So it'll be a unit one, right? So these are normal vectors, right? And so for closed surfaces, so when the surface is closed, we're gonna take a convention. When you hear if it's closed, when you hear take the positive orientation, it means that the vector you're gonna choose because remember you had two choices, right? The one that is outward and the one that is inside, the one that points to the inside. When you hear positive orientation, it means that you choose always the one that goes outside, right? Because it only makes sense for closed surfaces. Because if its surface is not closed, there's no way I can tell you, okay, choose the one that points to the outside, but depends on from your depends of your point of view. If you see from the above, well, it's gonna be outward, but if you see it from below, it's gonna be on the other side. So it doesn't really make sense when the surface is not closed. But when the surface is closed, intuitively, you can pretty much know if it's the one that is outside the surface is the one that is not bounded, right? So it points to the exterior of the surface. So this is the positive orientation. Um, so this is just an example of the sphere, but from this one, we're going to extend it to all the closed surfaces. For the closed surface, the orientation, so this is always going to be true in our case. The orientation you're going to take for all closed surfaces is that the positive is the one the normal vectors point outward of from outward point outward, and the negative orientation is the one for which the normal vectors point inward. Okay, so this is terminology you have to keep in mind. If we hear positive one for our closed surface, it means that it's outward. We're pretty much never gonna use the negative one. It's always positive. I mean, unless you hear it, I don't know. Maybe the other instructor will include some exercises on this. I have no control over that, but as far as I'm concerned, when I'm gonna include exercises on this, I'm gonna always use the positive one because there's no reason I'm gonna confuse you with the negative one. It's the same calculation basically. I mean, the only mistake you can make with this kind of calculation is gonna get a negative or a positive sign. Because when you do the integrals and you have the wrong normal vector, the minus or plus you're gonna carry out with you for the whole calculation. So by the end, you're gonna either get plus or minus, and it's not really that problematic. As I say, it's unless you are an engineer or something uh, caring for something really real life, but it's not that a problem. I would say, but it depends on the TA. Some TAs are like I cannot control the TA. The grader will decide, but make sure you don't make any mistake. Okay, surface integrals. All right, so that's pretty much it for oriented surfaces. Now we're gonna use this to talk about surface integrals for vector fields. Yeah. Uh, this should take us around, not that much. I think today I will talk about this, and then I will talk about the flux version of Green's theorem. I didn't talk about it, but you're gonna need it for the problem set, right? Because um, Christopher, who is the other instructor, he proposed that exercise, and I didn't know that I needed to tell you about that. So I need to talk to you about another version of Green's theorem, and you're gonna need it for that exercise. So it's pretty much important to talk about that if we decide to include it in the assignment for. All right, so let me take a break right now, I think, just to make sure that I'm gonna do it in one shot. Okay, So I'm gonna take a break right now, and then after the break, I'm gonna talk about surface integrals of vector field, and then the flux version of the Green's theorem. And yeah, next week we're gonna talk about Stokes theorem and divergence theorem, and that's it. Okay, so let me take a break right now. Okay. So surface integrals for vector fields. Okay, so now consider a vector field on R3 on an orientable surface with unit vector and so at this point I have a unit vector n, and I have a vector field f. And this is the point x, y, z. Okay. Then consider the function f, y, z, the scalar product of n with f, right? And remember, this is only if you take the scalar product, and this is a normal vector with unit one, it only gives you the component of f along the n direction. Okay? fx, yz gives the component of f along the direction n. Now, the reason the reason I did this is because I really want to simplify your life. Because I don't want you to think about this is a new kind of, this is not a new concept, this is not a new integral. It's really the one we saw before, but we're gonna give it a meaning. But then we can consider the surface integral, right? The normal one, the one I introduced before. It's the integral over the surface as of the function f, because remember, it was just a function ds, right? Right? Now I can write this one as the integral over s of f times n. By the way, remember that the scalar product does not really care about the order, right? ds, right? Now, the only thing here that is new is we're gonna write this, formally speaking, we're gonna write this as f scalar with n ds, right? right? Now, we have the surface, we have N, and this is some ds, some very small uh, element of area, okay? So instead of writing this as NDS, we're gonna write this as DS. Okay. So when you see this, it means this and means this. Okay. So ds will be actually a vector that points into the direction of n and has the length of it is an infinitesimal value of the area. So it's a vector that carries the direction of the normal vector, and also the norm of this vector will be the, the area of this little infinitesimal patch, or infinitesimal area, right? So this is called, this integral is called the surface integral of f over s. It is also called the flux of f over s. Okay, we have that the flux is the integral over s of f ds, which is the integral of f and ds, which is the integral of f scalar product ru rv rv times, what is this? This is the norm of ru rv dA, and now we have to integrate d, which is the parameterization domain. Now you can cancel out this one with this one. I will give you the integral over d f ru rv dA. So that's the formula you'll need to use. And d is the parameter domain. Okay. Oh no. Am I recording? Yeah. Am I recording? Okay, so I have two examples. Depending on how much time I will have, I will try to fit them into the last uh, 40 minutes of the course today. that if I don't, please go and read it. Because unfortunately for this week, you only have today and tomorrow to prepare for the quiz on Thursday. And please be aware that there will be questions on uh, on FDS. Okay. All right. There will be question on this. All right. Compute the integral over S FDS, where S is the sphere of radius 1 and centered at the origin, and F is equal to xy plus yj plus z square k. Okay. What is the other example? Yeah. So the first thing to do is we have the parametric representation of S, which is x equal to sine phi plus theta, y is equal to sine phi sine theta, and z is equal to cos phi, and theta is between 0 and 2 pi, and phi is between 0 and pi. Okay? Now, you have to, at any point of the sphere, what is the f? So f evaluated at r, this is r, right? So you have to substitute what you have here, 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 right? So it will be sine phi cos theta I plus sine phi sine theta j plus cos square of phi. Okay? What is r phi? R theta. all right? And make sure you have the right orientation for R, because this is a sphere. So whenever you have a closed surface, take the positive orientation. So in this case, it needs to be yeah, it needs to be the one that points outward, right? So don't. So if you take the cross product, it will give you sine square phi cos theta I plus sine square phi sine theta plus sine phi cos phi k, right? So this is outward, okay? But it's not normalized. But we're using this formula here with uv is equal to phi and theta. So the integral of f ds over s is the integral over d of f evaluated at the surface times r phi r theta. Okay, and so you have to multiply this and this scalar product. So it's sine cube phi. But here I'm doing some quick because you're gonna get cos theta square with sine theta square, and you will have the same. You will have the same sine phi cube. So you use the cos square plus sine square plus, right? And the other one, there is no simplification for it. There is sine phi plus cube of phi d phi d theta. Okay. All right, so at this point, there's really nothing else new. You just have to compute the integral. This is going to be 0. Well, it doesn't depend on theta, so it's 2 pi. The integral from 0 to pi of sine phi 1 minus cos square of phi plus cos cube of phi. Okay, and will be equal to 2 pi cos phi minus plus 1 over 3 cos cube of phi minus 1 over 4 cos 4 of phi between pi and 0, which is 2 pi 1 minus 3 minus 1 over 4 plus 1 minus 1 over 3 plus 1 over 4, which is 8 over 3 pi. Okay? And of course, what I was saying about if a surface is right, if as we did the last, because it's exactly the same surface integral we introduced earlier, right? Because the function inside is scalar product, and so if S is the union of S1, S2, S3, then the integral of S is again, you have to integrate over each side, right? Only thing is, only difference now is, okay, same for an arbitrary number of, okay? Because now the only thing is you have to compute the normal vector for each, we have to compute the, not the normal vector, but you have to compute the scalar product. And the other thing I want to mention is, of course, I told you that this one is useful and you can really use it everywhere. But sometimes this one is also useful, right? Why? Because sometimes you can see from the the graph that n will be, for example, I, right? For example, here, for example, if I have the plane, right, x, y, z, and my surface is some kind of surface, but one of the sides is some kind of circle on the z equal to 0. So what is the normal vector if it's the kind of surface that is like this, let's say? The normal vector here, you know, it's n, it's minus k directly because it's a plane, right? And if the vector field is, for example, something that lies on the xy plane, then the scalar product is 0, right? If this is f. So here you can immediately say that n is 0, right? Of course, it's going to happen also when you're going to compute this, right? RU, RV, but it'll take you much more work to take RU, RV, and then take the scalar product. But this one is also useful, depending on the situation, right? You choose this one or this one. But again, both of them are, you're basically the same thing. I mean, because anyway, you're going to have to compute ds, but you choose. It's really your choice. Okay. So that's how this is how it is done. Okay, so there is one last example. So please, I'm gonna upload the notes today. So please go over it. But I would like to give you, for the last 30 minutes, I would like to give you the flux version of Green's theorem. So this is some kind of not related to any of it. So here we're gonna be back to 2D. Remember, Green's theorem was only for 2D, right? So suppose you have a curve, right? The positive orientation, remember, is the counterclockwise curve C. Given by RT is equal to XT, I plus Y TJ plus, okay? Now it's 2D, right? Okay? Then the unit tangent vector at any point xt yt is t over the norm of r prime t and this one is gonna never be zero because remember we're only talking about smooth curves. So the normal vector, so here we have a point and we have the tangent vector, which is a unit one, and we have a normal one. So a normal vector, so the normal, so the normal vector n at x t y t with outward direction is n bar, n is equal to y prime t over r prime t I minus so well, the reason is because the scalar product is zero. And again, you have two choices here. But because this one is negative, and if you look at it like carefully, when x prime is increasing, it will be positive. So, and when x prime is decreasing, it will be positive. When x prime is increasing, it will be negative, right? So when it's like this, it's gonna be like this, and when it's gonna move around, right? So if you look carefully, this one is always the outward one. Right? You can give an argument just by looking at the increase, if x prime and y prime are increasing or decreasing. So I'm like moving along like this, or I'm moving along like this, right? And you're gonna see that it always goes like this. You're using the positivity of this of each component. By analyzing the sign of each component, you're gonna realize that it's always points outward. So what is this? So here, please don't be confused. We are in 2D, and this is a line integral. It really looks like the one we just did right now, but it's really really a 2D dimensional case, right? So this is really the ds, not the surface. It's the length of the curve. So what is this? And this is just the normal line integral you used to do. So the curve, this is f, and what is ds? What is ds? ds is, there's really a lot of similarities between 2D and YT, right? Because what is ds? It's really the r prime t. Go back to the formulas we introduced earlier, right? Like, and look at these striking similarities. This is just square root of 1 plus x prime t squared plus y prime t squared, right? And compare this to the dA, to the partial derivative we did with respect to the parameter, the x and t, x and y. And here instead of, here it's not even, sorry, it's not even ds, right? Because here it's dt. Remember, when we were in the 3D case, this one dA, because the parameter space is a 2D space, so you have, it's a dA, it's an area. Now here the parameter space is a one-dimensional space, so it's dt. So there's a lot of similarities between the formulas. And so what is this? So I forgot to tell you what is this is some curve and t is between a and b. So this is the integral from a and b. Yeah, and also I forgot to tell you that f is some vector field p I plus q j. So it's p times r prime, p evaluated at the point xt, yt, which is evaluated at the curve, on the curve, times y prime plus, oh, sorry, minus x prime t times q xt yt. Let me write this. So f is some p xy I plus q xyj. So this is equal to the integral from a to b of p evaluated at the curve, on the curve, y t, y prime t minus x prime t q x t yt divided by r prime t, right? And the whole thing multiply by r prime t norm dt. Now you can cancel out these two. It's AB. We're gonna drop off the notations here. So it's P y prime of t minus x prime of t q dt, right? Now this is AB. Now when you multiply y prime by dt, it gives you p dy minus q dx, right? Now, and this one, oops, becomes on the curve, right? So we're going backward. Okay. So now what the thing is, if you apply Green's theorem, but for the new for this function here, instead of q, right? The Green's theorem will tell you that this is the integral of all the domain D. The domain D is this one. So go back to Green's theorem and remember what it says. It says b dy q dx is d y dx of it's dy of p minus dy dx minus q, the whole thing dA by Green's theorem, which is equal to the integral of d dy p plus dx q. Okay. Now this is just the integral over d of the divergence of the vector field f dA. Right? Remember, what is the divergence of? Because f is p I plus. Oh, sorry. What is it that am I confused here? Uh, oh, wait, hold on a second. Uh, mhm. Let me just see if it's a typo. My notes. Wait. That is very strange because it's supposed to give the divergence of the field. which is not this one. I don't know if someone can see where I made the error. It's supposed to give the wait. If you take F, yeah, okay, it's P right now is dx, yeah. So you apply Green's theorem to this one, which is this is P, this is yeah, yeah. Wait, I'm sorry, I'm a bit confused. So give me 1 second. Hmm. Yeah, yeah. Okay. Sorry, sorry. I was just confused here, which is legitimate. So here, let me write this one as this is the integral over c of minus q dx plus p dy, right? Now by Green's theorem, right? Remember what it says. It says this is integral. Now you apply it to this function here and this function here is the integral of del p del x, okay, minus del y minus q dA. So this is Green's theorem. Now if you write this is del x p plus del y q dA, which is the integral over d of the divergence of f dA. Because remember, the f is pi plus qj, and the divergence, we did it for 3D case, but there's also the divergence. I mean, there's nothing that prevents you from doing it in 2D case. So it's just dx, the first component, dy, the second component, right? So this equals integral over c f and ds, okay? And this is called Okay, this is called flux version of quiz theorem. Or the book calls it, I think, the book calls it uh, the vector form, I think. But in the problem list, this is the one you'll need. It's called flux version. There is another version with the curl, but we're gonna see it the next week when we'll discuss Stokes theorem. So that's it. Now you have to use this one for the problem list. Okay, so this is, we still have 5 minutes, but I think I'm just gonna end it here. Maybe I need to tell something about so the quiz, we didn't send an email this week. I forgot to send that. But this week, so today, as I told you yesterday, it's gonna be about what we did the last week, conservative fields, 3D. But anyway, it's always the same. The quiz is always about what we did the last week, except for Thursday. So it's gonna be around the surface, so review surface integrals, so review the tangent plane, review parametric surfaces we did yesterday. You have to review surface integrals. The first one we discussed the last one, yesterday, and the new one with the orientation and all of that, right? And the example, right? And I would suggest to highly go over this example again. Which one? So as I said, you'll need this kind of surface integrals with the vectors and n, and the one with just ds. Make sure you understand which one. Yeah, this one. Just make sure you understand it. Go over it again, and this understand how I did all of that calculations and how I got the parametrics. Understand how I got the parametric equation for that cylinder, that oblique cylinder, and then that's it. So be aware that for the other students, this week is the last week, but for us there is one more class that is left for the next week on Monday, and that is gonna make up for the one we missed the last week. So what is the syllabus for assignment? Assignment for so someone is asking what is the syllabus for assignment 4? I'm not sure what you mean by that. You mean what will be covered? Is this your question? Like what will be tested on? Well, this we haven't discussed this yet, so we'll get back to you with more information about that with an announcement. But we're gonna try to make it easier because we have had some feedbacks that assignment 3 was a bit more difficult. So we're gonna make it a little bit more easier, but still you will have to study everything. And we're gonna try to put more focus on the last topics, surface integrals and all of that. But we haven't decided yet what are we gonna include some previous questions or not. Okay. All right, so this ends the class for today. See you next week. Don't forget the next week. All right.